friends, so let's begin the very discussion of the JEE Advanced Pattern Exercises for complex numbers and quadratic equations. The first question says that modulus of Z and modulus of W is exactly the same. Here, if it is equal to K and alpha is given by Z minus W bar upon K square plus Z W bar, then real part of alpha is what? Now see, the moment I show that alpha plus alpha bar is 0, this itself means that real part of alpha is 0, right? Keeping this in mind, if I consider alpha bar, if alpha is this, alpha bar is Z bar minus W bar bar, which is W, upon K square bar, which is K square, plus Z bar W bar bar, which is again W, right? Now it is given to you that mod Z equals mod W equals K. Mod Z equals mod W equals K. This means mod Z square equals mod W square equals K square. This is ZZ bar, this is WW bar equals K square. So Z bar is K square by Z and W is K square by W bar. So here if you incorporate those values, Z bar is K square by Z, W is K square by W bar, whole upon K square plus Z bar into W. So Z bar is K square by Z and W is K square by W bar. Simplify this, what do you get is alpha bar is K square common W bar minus Z whole upon, again you can see K square ZW bar plus K square into K square. So K square can come out common and this is what you have. This gets cancelled, you are left with W bar minus Z upon ZW bar plus K square, which is nothing but minus alpha. Once you get this, you have got alpha plus alpha bar is 0, which means real part of alpha is 0, and the question was what is the real part of alpha, and so your answer is that it is 0. Clear? Moving on to the next question, we have if Z1 or Z and Z2 are Z1 itself are non-zero complex numbers such that mod Z1 equals mod Z2 equals mod of Z1 plus Z2, then Z1 by Z2 can be what all values among these? See, now over here you need to very clearly understand that mod of Z1 by Z2 is actually equal to mod Z1 upon mod Z2. So if you are given this, this means mod of Z1 by Z2 is actually 1. And you are also given this, that means mod of Z1 plus Z2 upon mod Z2 is 1. This can be written as whole mod of Z1 by Z2 plus Z2 by Z2, that is 1. So what do you mean by this equals this, which is equal to 1? That means I can write this as Z1 by Z2 minus 0 plus 0 iota equals Z1 by Z2 minus 1 plus 0 iota, and this is equal to 1. This means Z1 by Z2's distance from this complex number is same as its distance from this complex number, which is 1. That means Z1 by Z2 lies on the perpendicular bisector of the line segment joining 0 plus 0 iota and minus 1 plus 0 iota. So if that is the situation, it's pretty simple to understand. This is 0 plus 0 iota or 0 comma 0 ordered pair. This is say minus 1 plus 0 iota, then the perpendicular bisector is this. What is this point? Minus half comma 0. Z1 by Z2 is a complex number lying somewhere on this line. Z1 by Z2 lies on the perpendicular bisector of the line segment joining -1, 0 and 0, 0. That means real part of Z1 by Z2 for sure is -half. So what is Z1 by Z2? It is -half plus some a times iota. I don't know what this is. But I know that Z1 by Z2's distance from 0 plus 0 iota is 1. This means magnitude of Z1 by Z2 is 1. So it means square root of this square plus this square is 1, or I can say 1 by 4 plus a square is 1 square, which is 1. So a comes out to be, a square is 1 minus 1 by 4, which is 3 by 4. So a is plus minus root 3 by 2. If a is plus minus root 3 by 2, Z1 by Z2 is coming out to be -1 by 2 plus minus root 3 by 2 iota. 1 by 2 you take out common, you have -1 plus minus root 3 iota, which is nothing but omega and omega square. So Z1 by Z2 is coming out to be option number B and C, which is omega and omega square. Next question, let's see what is it. Modulus of complex number whose reciprocal is given by the first column is what? Match it with the complex numbers given in the second column. Let's do it. First complex number is 1 upon a plus 1 upon b plus iota c. If you take out the exact complex number, it is b plus iota c plus a. So it is a plus b plus iota c upon a into b plus iota c. This is my reciprocal complex number. So mod of this is mod of this, which is mod of the numerator upon mod of the denominator. Mod of the numerator is under root a plus b whole square plus c square, and denominator is mod a common, and then magnitude of b plus iota c, which is b square plus c square, is 1 by mod z. So mod z will be what? It is mod a into under root b square plus c square upon under root a plus b whole square plus c square. So mod z in this case turns out to be mod a times b square plus c square under root upon under root is a plus b whole square plus c square. So a gets matched to r. Clear? Then you have 1 upon a minus iota b minus 1 upon a minus iota c. Let's do that. It is a minus iota c minus a plus iota b upon a minus iota b into a minus iota c. Clear? A gets cancelled, you have iota common, b minus c upon a minus iota b, a minus iota c. So magnitude will be what? Magnitude of this upon magnitude of this, right? Mod of iota is 1, so this just becomes mod of b minus c upon under root a square plus b square into under root a square plus c square. So you basically get mod z equals to reciprocal of this, which is under root a square plus b square into under root a square plus c square upon mod of b minus c. So b gets matched to p. After this, what is it that you have? Let's see. You have a minus iota c plus a minus iota b, right? So you basically have a minus iota c plus a minus iota b upon a minus iota b into a minus iota c. So you have what? A plus a is 2a minus or plus iota, or let me take it minus iota times b plus c. Why? Because it is minus iota b minus iota c whole upon a minus iota b, a minus iota c. When you take the mod, you basically get under root 4a square plus b plus c whole square whole upon under root a square plus b square into under root a square plus c square. Right? So, over here if you try to understand, from here what I can do is, if you see R, yes, so R and Q have already been taken. I am left with what? This is P. So, R and P have already been taken, I am left with Q and S. If you try to understand what is this particular point trying to say, it is saying 1 upon A minus iota B plus 1 upon A minus iota C. So, this becomes A minus iota C plus A minus iota B, which is 2 times A minus iota times B plus C. So, it is A plus A minus iota times B plus C, okay. Try to decode how basically you are going to move ahead with this step to actually match it to the correct entry in the second column, and then we are going to get back with the question. Okay guys, so in here there is a small correction. Here it will be B upon A plus iota B plus C upon A minus iota C. Now if you try to decode the correct option, what would that become? It will be 1 by Z means AB minus iota BC plus AC plus iota BC whole upon A plus iota B into A minus iota C. This gets cancelled, you are left with A times B plus C upon A plus iota B into A minus iota C. This is 1 by Z. So, the magnitude will be magnitude of this upon magnitude of this, which will be what? Magnitude of A, magnitude of B plus C upon under root A square plus B square into under root A square plus C square. So, if you see, S happens to be the correct option for this, so C gets matched to basically S. Last is 1 upon A plus iota B plus iota C. So, 1 upon A plus iota times B plus C, this is very easy. This is 1 upon under root A square plus B plus C whole square. So, your answer is under root A square plus B plus C whole square, which is Q. So, D gets matched to Q. Moving on to the next, we have, if the equations this and this have a common root, then which among these is the correct option? Okay, so alpha is suppose the common root, okay. So, alpha will satisfy this and this. So, you have alpha square plus B alpha plus C is 0, and you also have B alpha square plus C alpha plus 1 is 0. Just multiply this by B, the entire first equation by B. What do you get? So, you initially had alpha square plus B alpha plus C is 0. You multiplied it by B throughout and then perform this subtraction. You basically get this getting cancelled. You have B square alpha minus C alpha. So, it is B square minus C plus BC minus 1 equals 0. So, alpha turns out to be 1 minus BC upon B square minus C. When you plug this value of alpha in here, you basically get 1 minus BC whole square upon B square minus C whole square, this is alpha square, plus B into alpha plus C is 0. Okay? Now next what do you get is, once you have this being satisfied, when you eventually solve this out, you get 1 plus B plus C. After that you have BC plus B plus C, 1 plus B plus C, BC square plus B square plus C square, minus BC minus B minus C equals 0. Clear? Which you can write as what? Half of 1 plus B plus C into, you will have B minus C whole square plus B minus plus C minus 1 and B minus 1. This is 1. Okay? So, you will have B minus C whole square plus B minus 1 plus C minus 1. That's what you're going to have. Okay. So here when you get this on simplification, you can just modify it into this, and therefore this is going to imply that for this equation to be equal to 0, either this is 0 or this is 0, which eventually is going to give you your answer that either this is 0 or this is 0. So it is these conditions which are going to imply having these two quadratic equations to have a common root. Now when I move ahead with the next question, we have A, B, C are in GP. A, B, C are in GP, then the equations this and this have a common root. Then what happens? Okay, so A, B, C are in GP, so you have B square equals AC, or B is root AC. So this equation becomes what? This becomes AX square plus 2BX 2 root AC into X plus C equals 0. C you can write as root C whole square, A you can write as root A whole square. This becomes root AX plus root C whole square. So X turns out to be minus root C by root A with multiplicity 2. Because this is a common root, so it will satisfy the next equation also. So you have dx square, d and square of this, which is C by A, plus 2ex, 2ex, x is minus root C by root A, plus f equals 0. Send this to the right hand side, you have dc by A plus f equals 2e root C by root A. Divide throughout by C, you get d by A plus f by C plus 2e by, or this is equal to 2e by root AC. But root AC is B, so this becomes 2e by B. So you are getting twice of e by b is d by A plus f by C, which means d by A plus d by A, e by b and f by C are in AP. So you are getting d by A, e by b, f by C are in actually arithmetic progression. Then you have alpha and beta, the roots of this equation, then equation whose roots are the respective ones given in the first column is what? Let's see. You know this transformation. If you want an equation whose roots are minus 1 by alpha, minus 1 by beta, negative of the reciprocal of the roots of the given equation, you basically replace x by minus 1 by x in this equation. So it is a into minus 1 by x whole square, which is a by x square, minus b by x plus c is 0. So you get a minus bx plus cx square equals 0. That is cx square minus bx plus a, so a gets matched to r. Clear? Then you have minus alpha minus beta, replace x by minus x. Replace x by minus x, you get ax square plus bx plus c is 0. So you get ax square minus bx plus c, so this gets matched to s. B gets matched to s, alpha square, beta square, replace x by root x. So you get a root x whole square plus b root x plus c is 0. So you get ax plus c equals minus b root x. Right? Square both sides, you get a square x square plus c square plus 2acx equals b square x. So you get a square x square plus 2ac minus b square x plus c square equals 0, which is this equation, that is Q. Then you have 2 alpha and 2 beta, replace x by 2. When you do that, you get a x square plus bx plus c. So you get ax square by 4 plus bx by 2 plus c equals 0. So you get ax square plus 2bx plus 4c. Ax square plus 2bx plus 4c, that is p, so d gets matched to b. Clear? After this you have statement 1 and statement 2 given to you. If a, b, c are real numbers, 2a plus 3b plus 6c is 0, then equation this has at least one root in 0, 1 closed interval. Now for this, the moment roots come into picture, we basically recall the Rolls theorem very frequently. What do? We define a function fx such that its derivative is ax square plus bx plus c. So I talk about 1 by 3 ax cube plus 1 by 2 bx square plus c. Now this particular function is continuous on closed interval 0, 1. It is differentiable on open interval 0, 1. And if you talk about f of 0 is clearly 0, and f of 1 if you talk about, it is a by 3 plus b by 2 plus c. If you take out the LCM as 6, you have 2a plus 3b plus 6c. And 2a plus 3b plus 6c is already given in the question to be 0, so you get this also as 0. F of 0 is 0, f of 1 is 0. In 0, 1 closed interval, it's continuous. In the open one, it is differentiable. Therefore, there exists alpha such that f dash alpha is 0. F dash alpha means a alpha square plus b alpha plus c is 0. But ax square plus bx plus c is the equation given to you. That means alpha is satisfying that equation, which implies alpha is a root of ax square plus bx plus c equals 0. So yes, in 0, 1 interval, ax square plus bx plus c definitely has a root. So this equation, this statement is true. Next says, if a continuous function f defined on R assumes both positive and negative values, then it vanishes at least once. Yes, of course, this is true that if a function is assuming both positive and negative, so to go from positive to negative, it has to intersect x-axis at least once, and therefore it definitely has a root at least. But this is not giving you any kind of implication for statement 1. So I can say that statement 1 is true, statement 2 is true, statement 2 is not a correct explanation for statement 1. Let's move on to the next question. Again, it is related to the statement. What does it say? If all the 4 roots of this equation are positive, then a is 6 and b is 4. Let's see. All the 4 roots of this are positive. So let x1, x2, x3 and x4 be the 4 roots. They are all positive. You know that sum of the roots will be what? It is minus of coefficient of x cube upon coefficient of x to the power 4. So minus of minus 4 by 1, which is 4. And if I talk about the product of the roots, it is constant term upon coefficient of x to the power 4, which is 1 upon 1, which is 1. So I can say 1 upon 4 times x1 plus x2 plus x3 plus x4. What is this? This is arithmetic mean of the 4 positive numbers. What is this? This is 4. So 1 by 4 into 4 is 1. And if I talk about x1 into x2 into x3 into x4 to the power 1 by 4, this product is actually 1. 1 to the power 1 by 4 is 1. This is also 1, and this is nothing but geometric mean of x1, x2, x3 and x4. Both of them are coming out to be the same. Arithmetic mean comes out to be equal to geometric mean if and only if all these terms are equal to 1, right? And therefore my equation, whose roots are these 4, becomes what? X minus 1 whole to the power 4. When you expand this by binomial theorem, you basically get a, that is the coefficient of x square comes out to be 6 and coefficient of x comes out to be minus 4, so b is actually 4. So statement 1 very nicely happens to be true. Also, if polynomial equation has 4 positive roots, then the polynomial equation p dash x has 3 positive roots. Now see, polynomial is always continuous and differentiable throughout the entire real line. If it has 4 positive roots, between any 2 consecutive positive roots will be lying at least 1 positive root of its derivative. So if there are 4 positive roots of px, p dash x is also a polynomial, it is also continuous and differentiable, right? And that particular polynomial is going to have 3 positive roots, because between any 2 positive roots of px lies at least 1 positive root of p dash x. Clear? So there are 4 positive roots of Px, so at least 3 positive roots will be there of P dash. And therefore statement 4 is also true. This is following by Rolls theorem, but this is not giving a correct implication for this. So I'll say statement 1 and statement 2 are true, but statement 2 is again not a correct explanation for statement 1. Next question says that the smallest value of k for which both the roots of this equation are real and distinct and have the value at least 4. Okay. So this is pretty simple. Here is a quadratic equation, and you know when does the quadratic equation have real and distinct roots, when its discriminant is strictly positive. So b square, this is b square minus 4 into a into c. This is positive. This when you solve, you get 64k square minus 64k square plus 64k minus 64. So 64 common, k minus 1 is positive, that means k minus 1 is positive, k is greater than 1, but k is an integer, that means k is greater than equal to 2. Also suppose alpha and beta are the roots. It's given that the least value they have is 4, so alpha is greater than equal to 4 and beta is greater than equal to 4. Then alpha plus beta is greater than equal to 8 and alpha into beta is greater than equal to 16. Sum of the roots is minus b by a. Sum of the roots is 8k by 1. So alpha plus beta is 8k and, or this is greater than equal to 8k, and alpha into beta is c by a, which is 16 into k square minus k plus 1. This is greater than equal to 16 into k square minus k plus 1. This is, I can say this is greater than equal to 16 and alpha plus beta is 8k. 8k is greater than equal to 8. So you get k is greater than equal to 1 and k into k minus 1 is greater than equal to 0. From here you are going to get that. This is 16k square minus 16k plus 16. So this gets cancelled out. You get 16k square minus 16k is greater than equal to 0. So 16 comes out common. You get what? K square minus k is greater than equal to 0, or k minus 1 is greater than equal to 0. From here you basically get the common portion is this. So k is greater than equal to 1, k is greater than equal to 2. The minimum value that you can get is k equals 2. So the integer associated to this question is 2. Next question says what? Let a, b, c be complex numbers such that a plus b plus c is 0. Mod a plus mod a equals mod c plus mod c. So all these three terms a, b, c have the same modulus, that is 1. Then what is the value of this expression? Okay. If I talk about mod of b minus c whole square plus mod of b plus c whole square, you know these identities. This you know, when you expand, you get twice of mod b square plus mod c square, right? This is mod of b minus c whole square. Now mod of b plus c, see b plus c is minus a, so mod of b plus c is mod of minus a whole square. This is twice of mod b is 1, mod c is 1, so this is 1 plus 1. Mod a is actually 1, so 1 square is 1. So you get mod of b minus c whole square is 2 into 2, 4, 4 minus 1 is 3. So b minus c mod is root 3. Exactly in a similar fashion you can show mod of a minus b is root 3 and mod of a minus c is root 3. The moment you show this, you get mod of a minus b whole cube, that is root 3 whole cube. Root 3 whole cube becomes 3 root 3, right? Plus again 3 root 3 plus 3 root 3 minus thrice of mod of a minus b, which is root 3 into root 3 into root 3, so 3 root 3. This is 0. So you get this plus this plus this minus thrice of this, which is 0. Integer associated to this is 0. So practice them very nicely. That's it from my side. Thank you.